Hello everyone. Today we will discuss about the Liouville theorem. So what is the statement of Liouville theorem? You can see here I write the statement of Liouville theorem. But to understand this theorem or this result, first we need to understand some basic concepts of related to entire function and related to bounded function. So Liouville theorem says if any entire function f of z is bounded for all value of z, then it is constant. Okay, it is a simple statement. So what is the meaning of entire function? And you can underline the entire function and bounded function. Okay, so if any function is entire, it means the function is analytic on the whole complex plane. The function which is analytic in whole complex plane is called the entire function. Okay, so what is the analytic function? I have already discussed in the previous video what is the analytic function. So the function which is entire in the whole complex plane is called the entire function. And bounded function means what? If function is bounded by the two limits, bounded by the 2 points, or bounded by the two integers. For example, if you have a sine function, as you can see in the real analysis, sine function is bounded by +1 and -1. So as you can see, if we are talking about in a real analysis, so this is the graph of sine function. Okay, it's a graph of sine function which is bounded by +1 and -1. The range of the function is bounded by +1 to -1. It means the sin x function or sine function is bounded by +1 and -1. Okay, similarly any function bounded by which has a upper bound and lower bound is called the bounded function. Okay, and we can denote the bounded function as, suppose f of z is bounded, so we can write f of z mod of f of z less than equal to suppose any integer k. Okay, it means mod of z, it means z lies between -k to +k. K is any integer. Okay, so this is a basic definition of bounded function and entire function. Entire function means, as I have already told you, it is analytic in the whole complex plane. Okay, so simply as you can see here, the Liouville theorem says that if any function is entire and bounded, then it is constant. Okay, now you can see the proof of this Liouville theorem, which is very easy. So proof. Now we start the proof of the Liouville theorem or Liouville result. So as you can see, the given f of z is entire and bounded. It means f of z is bounded by k. Okay, so we will show that f of z is constant. If we are able to show f of z is constant, it means we have to prove the given function is the given entire function, the given f of z is entire and bounded, then we will show it is constant. Okay, so the result of the theorem of Liouville theorem. So what is the constant function? Constant function, if I draw the constant function in real analysis, so you can see here, this is the constant function. Okay, f of z or f of y, f of x, y equal to f of x. It means for every value of x, the whole values of f of x are equal or constant. Okay, so corresponding to, suppose this is 1, this is 2, this is 3, this is 4, this is 5. So corresponding to 1, you get f of 1, corresponding to f of 2, f of 3, f of 4, f of 5, likewise, and so on. Okay, so and if you want to draw this constant function, so you can draw, suppose here write 1, 2, 3, 4, and 1 is mapped in, suppose a is any point in codomain, and 2 is also, and 3 and 4. So whole points of the domain is mapped on the single point of codomain. So, or you can say simply, if f of a equal to f of b, it means the image of the points a and b are equal for all ab belongs to z. Z means the set of complex number. Then you can say the function is constant. Okay, it's a simple definition of constant function. So we need to prove f of a equal to f of b for all of ab belongs to z, where z is a complex variable. Okay, so first we remove this thing and then start to prove the theorem. Okay, now because f of z is constant, it means, and f of a equal to f of b, we need to show. So suppose we draw this graph like this is the radius of r, and circle, this is a circle with radius r and center 0. So center is 0 0 and radius suppose is r. Okay, and suppose a and b are 2 points inside this circle, a and b. Okay, now by the Cauchy integral formula, I know that if 2 points lies inside the analytic function, then the value of that point is given by, so we can write here by Cauchy integral formula. Cauchy integral formula. What we know that, what is the value of f of a? This is the point, the value of function at point a is given by 1 upon 2 pi I, 1 upon 2 pi I integration f of z upon z minus a dz. Similarly, what is the value of the function at point b, which is given by f of b equal to 1 upon 2 pi I integration over the curve C and over the curve C f of z upon z minus b dz. Okay, now suppose this is the equation number A and equation number B, or you can write equation number 1 and this is equation number 2. Okay, so to prove f of a equal to f of b, it means f of a minus f of b equal to 0. Okay, so by first and second we can write here f of a minus f of b equal to what? 1 upon 2 pi I integration f of z upon z minus a dz minus 1 upon 2 pi I, the value of f of b, integration over c f of z upon z minus b dz. Okay, so we can take the common out 1 upon 2 pi I, so you can write here 1 upon 2 pi I integration, or you can take the common f of z, so integration over c f of z, and we can write here 1 upon z minus a minus 1 upon z minus b dz. Okay guys, which is equal to 1 upon 2 pi I integration over the curve C f of z minus b, cross multiplication z minus b minus z minus a upon z minus a and z minus b dz. Okay, which is equal to 1 upon 2 pi I integration over c f of z minus b minus z plus a upon z minus a, z minus b, z minus a, z minus b dz. You can see the z and z are cancel out, so we can write a minus b upon z minus a, z minus b, and a minus b is a constant, so you can take the outside from the sign of integration. Okay, so we can write in the next page, which is equal to 1 upon 2 pi I, 1 upon 2 pi I integration over c, and simply we can write here integration over c and the value of a minus b upon z minus a, z minus b, a minus b upon z minus a, z minus a z minus a and z minus b, and f of z also. So this is f of z dz. So a minus b is a constant, so we can take the outside from the integration. A minus b upon 2 pi I integration over c f of z upon z minus a and z minus b dz. Okay guys, so we are simply solving the integration. Okay, so this is equal to as you can see fa minus fb equal to this thing 1 upon 2 pi I a minus b upon 2 pi I f of z minus a z minus b dz. But we know that the function is constant. Function is constant means f of z must, the mod of f of z must be less than or equal to k. Okay, so f of a minus f of b equal to a minus b upon 2 pi I integration over c f of z upon z minus a and z minus b f of z. Okay, so because function is constant, so we can take the value mod of f of z is equal to k. For this we need to first take the mod both side, okay, which is equal to mod of f of a minus mod of f of b modulus equal to a minus b modulus upon 2 pi modulus I modulus, because 2 pi is a real number, so modulus of 2 pi is again 2 pi, and a minus b is also a real number, so a minus modulus of a minus b again modulus of a minus b again a minus b. But I is a complex number. I is the iota means it is a complex number, so mod of iota equal to 1. Okay, so you can write here to understand mod of I equal to 1. Okay, and integration. Okay, when we take this integration inside the integration, this mod inside the integration, then we use the here less than equal to, otherwise we use simply equal to sign. Okay, so we write here f of z upon z minus a and z minus b inside modulus sign in the integration and dz under modulus, and we can write here less than equal to. This is the property of the modulus. Okay, so which is equal to what? Which is equal to mod of f of a minus f of b just a minute, mod of f of a minus f of b equal to what about my pen? Okay guys, so we can write here again, simply we write mod of f of a minus f of b modulus less than or equal to what? Less than or equal to a minus b upon 2 pi I, mod of I equal to 1. So we can write here a minus b upon 2 pi and integration we can write here, because we take the modulus sign in both sides, so mod of whole the mod equal to mod of f of z upon mod of a minus b, z minus b and z minus. So we can write here f of z modulus of f of z upon z minus a modulus z minus b and modulus dz. Okay, modulus of dz, which is equal to f of a minus f of b modulus less than or equal to a minus b upon 2 pi and k upon mod of z minus a z minus b dz modulus of dz, since mod of f of z less than equal to k as the given function is bounded. So we can write in the place of mod of f of z equal to k. Okay, now because our function is entire, so we can't take only the circle of radius r. Okay, as you can see, we have the radius, we have the circle with radius r, but because function is entire, it means the function is analytic in the whole complex plane, not only the circle which have the radius 1. So we can extend r as a infinity. It means r radius with infinity. In infinity, it means the whole complex plane. Okay, not only the r means the not a fixed number but a whole complex plane. So we can take r as tending to infinity. Okay, so when we take the r as infinity, it means what? So you can write here simply mod of f of z, because we have take the z equal to r. This is the circle with radius r and center 0 0. Okay, so dz equal to what? Dz equal to mod of dz equal to r d theta. How? Because you can see here, if mod of z equal to r, it means z equal to r e to the power I theta. Okay, and dz equal to, it means differentiation of z, dz equal to r I e to the power I theta d theta. Okay, and mod of z equal to mod of z equal to mod of r, mod of I, mod of e to the power I theta, and mod of d theta. Okay, so mod of r equal to r, because r is a real number, and mod of I equal to 1. So r into 1 means r. Mod of I e to the power I, again 1. The value of e to the power I theta equal to cos theta plus I sin theta, and the modulus of e to the power I theta equal to 1, because modulus of cos theta plus I sin theta equal to 1. Okay, and modulus of d theta, again d theta, because d theta is a real. So dz equal to simply r d theta. Okay, so you can replace a minus b upon 2 pi integration we can take here, we can take k as a outside, because k is a constant, and dz equal to r d theta upon z equal to r. So we can take here r minus a, mod of r minus a, and you can write here r minus b, r minus mod of b, because you can write mod of a, mod of b, because this property, we can use the property z minus z2, mod of z minus z2 is greater than or equal to mod of z1 minus mod of z2. Okay, mod of z2. So we use this property here. So we can take r as a common. So you can write k a minus b upon 2 pi integration r d theta upon, we can take r as a common, so we write 1 minus mod of a upon r, and again we take r as a common, so here 1 minus b upon mod of r, sorry, mod of b upon r. Okay, and we can cancel r by r. Okay, so now to finding, because we need to approach the r as an infinity, because we need to take the r, the radius, it means r as an infinity, because our function is the entire, and entire function means that it is analytic on the whole complex unit, not only r but whole, so we can take r as infinity. So for this we need to take the limiting value of this integration as r tending to infinity. Okay, so we need to write the next page, mod of a minus b, mod of a minus b less than or equal to k times a minus b upon 2 pi limit r tending to infinity integration over c and d theta upon a minus 1 minus a modulus of 1 minus mod of a upon r into we can take, otherwise we don't need to take the r minus we do not take the common as r in r minus mod of b. Simply you can write r minus mod of b, r minus mod of r minus mod of b. Okay, now as r tending to infinity, this means this is the 0. Okay, so 1 minus 0 means 1, and when we need when r is infinity in this modulus, it means this is a whole infinity. So infinity into something is equal to infinity, so 1 upon infinity, it means 0. Okay, so which is equal to k times of a minus b upon 2 pi into 0. This whole integration is 0 as r tending to infinity. It means a minus b, f of a minus f of b, the whole modulus less than or equal to 0, implies that f of a minus f of b equal to 0. If the modulus of any number is less than or equal to 0, it means that number is equal to 0. Okay, implies that f of a equal to f of b, hence proved. It means for all ab belongs to z. Okay, so we have to prove the function is the constant. Okay, so as you can see, first we need to take the function is the entire and bounded, and we assume the function is constant, and we need to show that the function is constant. Function is constant means f of a equal to f of b for all ab belongs to z, and by the use of Cauchy integral formula, we have to prove this function is constant. Okay, as you can see, with the simple step we have taken, and you can see the f of a equal to f of b, the function is constant. It means the Liouville theorem is proved. Okay, so it is very important in the analysis part of it is a part of complex analysis, and it is also used the engineering mathematics. This statement is very important because only statement has some questions related to the statement, like a function is entire and bounded, which is constant or non-constant, and whatever about. Okay, and if a function is entire, then it is a constant or not, but it is needed, it is a need to first understand the function must be bounded, not only entire, but it must be bounded. If a function is entire and bounded, then it is implied the function is constant. Okay, this is the Liouville theorem. So guys, I hope it is clear, and if you have any query, please write in the comment section. Okay, and if you have any doubt, you can ask anytime in the comment section. Okay guys, okay, thank you so much again.